So, hello and welcome to today's lesson. So, this happens to be the eighth lesson in our study of Topology I, and today we'll be talking about metric spaces. Okay, so after going through the concepts, definitions, and taking explanations, um, the goal is to be able to solve this particular question here. All right, and don't worry, as we go through the definition, it will become very simple for you to solve that particular question. Okay, so this video has been made in a way that the concepts will be very simple to understand. They'll be explained in simple terms. Okay, so you're going to understand metric spaces at the end of watching the video. So don't forget to like the video if it helps you, and subscribe to the channel so that you'll be notified of future videos. So metric spaces, let's take an introduction. So one of the most common and useful types of topological spaces is the metric space. So metric spaces are topological spaces that result from having a means from measuring distance from 2 points in the underlying set. So that means when you talk about metric spaces, then we are always looking at a mean of measuring distance between 2 points. So maybe let's say we have a point x and a point y, and we want to measure the distance between these 2 points. That's when we apply metric spaces. Okay, so metric spaces play a major role in the mathematical field of analysis, and they appear in a variety of interesting applications. Okay, so yeah, they have a lot of applications, even in computer science and a whole lot. So we will discuss that in our next video under metrics and information. So we are talking about metric spaces. What's that metric space? Okay, so let's take the definition. So a metric on a set x is a function, and the function is given by what we can see here. So small d is such that s cross x maps onto r, which is the real number system. So with the following properties. So we have three properties which always have to be satisfied. So the first one says that the distance between x and y is greater than or equal to 0. Okay, for all x and y in big X, equality holds if and only if x is equal to y. Okay, so this is something, what this means is that, when you're measuring the distance between 2 points, there is no way you can get a negative distance. Distance is always positive. Okay, so that's the reason why it is always greater than or equal to 0. And the only time it will be 0 is when we are measuring the difference between you're measuring the distance of 2 points at the same point. Do you get it? Maybe let's say we have point x here, and we also have another point here, and you want to measure the distance between them. You're going to get 0 because they are the same point. Okay, so that's the reason why it says equality holds if and only if s is equal to y. If not, the distance between 2 points will always be positive. Okay, so that's what the first one says. Then the second one says that the distance between x and y is always equal to the distance between y and x. And that's true. So for instance, when I have a point x here and I have a point y here, the distance between moving from x to y is the same distance when you move from y to x instead. Okay, so that's what the second point says. And the third point says that when you have 3 points, so let's say we have 3 points x, y, and z. The distance between x, so the distance between x and y plus the distance between y and z is always greater than or equal to the distance between x and z. Okay, so let me explain that one too. So for instance, when you have these 3 points x, y, z, okay, you could see that with this particular one, the distance between x and y plus the distance between y and z will be the same as the distance between x and z. They'll be equal, right? So that's when the equality holds here. But let's say if we have something like this, there's our point x, there's our point y, and there's our point z. So let's draw something like a right angle triangle, right? So you can see that if this place is 3 and this place is 4, this place will be 5. So you could see that here the distance between x and y is 4. That between y and z is 3. And remember that one is 7 and is greater than the distance between x and z, which is 5. Okay, so I've been able to show you two cases where we can have it being greater than or being equal. Okay, so that's the definition, and I think the 3 points have been explained very well for you to understand. Okay, so now let's go to some important points for you to note. So note that D has the properties we expect when we measure distance between points. So the first point says the distance between 2 points is at least 0, and it equals 0 only when the points are the same. Okay, I've said that already. Then the second one says the distance from point x to y is the same as the distance from point y to x. And the last one says find the distance to travel from x to y and then y to z is never shorter than the distance to travel directly from x to z. Okay, so that's the third point, which has been explained. Okay, so now let's move on. So there is an example here. Okay, so we want to talk about the Euclidean matrix or the standard metric on R. So on our number system, we can define the distance between x and y to be this, right? So this is called the Euclidean metric or standard metric on R. So condition I and I are immediate. So from the definition, these first two conditions, they are immediate. So you would want to check for condition 3. So the triangle inequality can easily be verified by considering separately each of the orderings of the 3 points x, y, z. For instance, in a case that, right, so we have a case here that y is less than or equal to x and x is less than or equal to z. So here we can see that the distance between x and y plus the distance between y and z will be given as this, right? So since s is greater than or equal to y, it means that the distance between x and y will be given by x minus y, because we always have to get a positive result, right? We can't do it y minus x if we are going to get a negative outcome, because x is greater than or equal to y, or y is less than or equal to x. Okay, then the distance between y and z would also be z minus y, because z is bigger than y. Okay, so this is what we had here, right, is greater than or equal to z minus y, because you can see that here we are going to get a positive number here, right? And you're also going to get a positive number here. So because of that, when you add these two, it will always be greater than or equal to just what we have here, right? So that's the reason why you can find the second point here. So what we have here is greater than or equal to z minus y, and z minus y here is also less than or equal to. So that means that this z minus x here is greater than or equal to z minus y. And the reason why we are saying that is because sorry, this z minus y here is greater than or equal to this z minus x. So the reason we are saying that is that we have 3 points here, y, x, and z, and this happens to be the smallest. So that means when you take this y from z, what you will get will be bigger than when you take x from z. Okay, so that's the reason why z minus y is bigger than z minus x. Okay, sorry for the wrong statement I made earlier. So a slip of tongue. So you could see that then when we have this is the same as the distance between x and z, right? So that means that we've been able to prove the inequality. So we have the distance between x and y plus the distance between y and z is greater than or equal to the distance between x and z, which shows that the third condition is also satisfied, right? So that means we have a metric on R. So now we have an exercise that we have to tackle. So you can see the question there. So let the pair xd be a metric on a space. So for x, y in big S, right? So we define the distance between x and y to be what we have here. So now the first part of the question says we should show that D is also a metric on x. And the B part says that we should explain why no 2 points in x are distance one or more apart in the metric D. Alright? So before we can show that D is also a metric on x, that means we have to show that the three conditions are met. Alright? So when we're defining the metric space, we had 3 conditions. We have to check for each of them and make sure they are satisfied. So you could see that we said the distance between x and y is always greater than or equal to 0. Meaning, since we have something which is positive here, meaning the distance between x and y, all over 1 plus the distance between x and y will always also be greater than or equal to 0, because, for instance, if these places, if you have the distance between x and y to be, let's say, 1, you're going to get 1 over 1 plus 1, which will be half. As far as this is positive and this is positive, the whole of this will always give us something which will also be greater than or equal to 0. Okay, so saying this is greater than or equal to 0, it means that capital D, the distance, okay, so here I'm using capital D instead of small d, so the distance between x and y is always greater than 0, because capital D is given by this. So if this is greater than or equal to 0, then that means this is also greater than or equal to 0. So we've been able to show the first one. Then in the second one, we have to show that the distance between x and y is equal to the distance between y and x. Okay, so this is the same as that, meaning that the distance between x and y is the same as the distance between y and x. So always the first two conditions is very easy to get them, but sometimes the work is with the third one when you want to show the triangle inequality. Okay, so now the big deal is the third property. That is, we have to show that this thing holds, or that it is this thing which holds instead. Okay, alright, so the reason why this is the same as this, because here we are saying that the distance between x and y plus the distance between y and z is greater than or equal to the distance between x and z. So if we decide to bring this here, then that means to be less than this, right? less than or equal to. So we had a function, right? So we had a space, and the space was this. So we had something like this. So when you write this in a function form, it's the same as having a function of this form, x1 plus x. And you realize that this particular function is everywhere increasing on the positive rails, or it is monotonic increasing, right? Monotonically increasing. So it means that if x is greater than or equal to y, then the function f of x will also be greater than or equal to y. Okay, so we want to show the triangular inequality, right? So let's go ahead to show that. We are going to do some analysis here, so please look carefully and pay attention. Okay, all right, so we are saying that the distance between x and z, right, is given by what we have here per the map which was given to us in a question. Okay, right, and we are saying that is less than or equal to what we have here. So that means that we can write it. So when you write it, this is what we have. Okay, so this is less than or equal to this thing here. So we can decide to separate them. Okay, so we can decide to just take this part all over this and take this part all over the denominator. So that's what we can see here. So this thing here is equal to what we see here. We've just separated them with their, we separated the numerators and we have their denominators. You know, it holds in maths when you have something like 2 plus 4 all over 2. You know, this is 6 over 2, which is 3. You can also do it 2 over 2 plus 4 over 2. You still get 3. So that's why we can do something like this. All right. So you could see that here we had something here, and here too we have something here. But when it comes to the next line, we can't see this here. Here too we can't see this here. So the reason why you saw is that you could see here we had the equality sign, but we are having less than or equal to. So the reason why it is so is because, you know, the distance between y and z would always be positive. The distance between x and y will always be positive here. And because they are in the denominator, if the denominator is larger, that means that the value is going to be lesser, right? So that's the reason why 1 over 2 is always greater than 1 over 3 and is greater than 1 over 4. So you could see that when we take away this and we also take away this, that means that what we have here will be less than or equal to the distance between x and y over 1 plus the distance between x and y, then plus the distance between y and z all over 1 plus the distance between y and z. So that's the reason why here the inequalities the equality sign changes to this less than or equal to. Okay, then you know we can write this as this, and we can also write this as that from the mapping which was given to us in the question. All right, so that means we've been able to show that, hence we've been able to show that the distance between xz is less than or equal to that of the distance between that of xy plus that of yz. That's the triangle inequality. All right, so we've been able to show the third condition, meaning that we've been able to show that d is also a metric on x. Okay, then the second point says that we should explain why no 2 points in x are distance 1 or more apart in a metric d. So the explanation. So you know we had this, right? This was our metric. So since the distance between x and y is the same in both the numerator and the denominator, so what we have here is the same thing as we have here. So it means that, let me use arbitrary values to explain this point better. So for instance, if the distance between x and y is 2, we are going to get 2 over 1 plus 2, which will give us 2 over 3. If the distance between x and y is 3, we get 3 over 3, 1 plus 3, which will be 3 over 4, right? So you could see that because of the 1 plus 1 that we have here, always the denominator will be larger than the numerator. And if the denominator is larger than the numerator, that means always you're going to get something which will be less than 1, right? So that's the reason why you can never have 2 points in x which will be distance 1 or more apart in the metric d. I hope you get it. Right, so let me read what I wrote here for you. It says, since the distance between x and y is the same in both the numerator and the denominator, we would always have the denominator being larger than the numerator. So no 2 points in x will be distance 1 or more apart in d. Okay, so that's it with the metric space. If you didn't get anything, you can ask a question in the notification. I'm sorry, the comment section, and I'm going to reply you. Okay, so all the best and thank you.